Hello. So I'm very proud to announce the next one. Terence, who works on the Ruby team, will talk about Rust and how to make it, how to use it with mruby and the Windows friendly. And yeah, you know, you come from a long way from Texas, you like tacos, and please welcome my friend Terence. Thank you.
Thank you, Christoph. Yeah, so I'm here to talk to you about mruby, Rust, and Windows, probably all very niche things to probably many of you in this audience. I recently got a Windows laptop at work, so I'm pretty big on a Windows High. I did half these slides on Windows. Like Christoph said, I'm Terrence. I go by Hone02 on Twitter. I'm famously known for my blue hats. I have blue hat stickers here if you would like some. I work at Heroku. Work on Ruby stuff there, as well as some other things. I brought some shirts and stickers and stuff, so come say hi. I'd be happy to give you some swag if you would like. Come from Austin, we have some amazing tacos. If you're ever in town, definitely hit me up and I'd be happy to take you out for some tacos. I think only like 5 people actually, for all the talks I've given, actually hit me up on this. And I also run a conference in town called Keep Ruby Weird, so please submit the next time we open our CFP for that. And that's kind of it for the intro, so let's actually get to the meat of the talk. So today we're going to cover kind of the state of Windows and Ruby. Hint, not a very good one. Go through a quick intro of mruby and Rust, because I think many people here are probably not familiar with either or both of those technologies. Talk about how to use mruby with Rust, and then kind of any future work and what we have going on with all that stuff going forward. So with Ruby on Windows, the Heroku CLI used to be actually written in Ruby, and then we rewrote it in Go, and then we're looking at various plugin systems, and Ruby was on the table at one point, but it got quickly moved off because of the fact that we have, I think like 50% of the people that hit Dev Center, which is our documentation site, are actually Windows users. And so the fact that Ruby does not work very well on Windows made it where it wasn't actually a viable option anymore, even though we had a ton of people in the house who didn't like JavaScript, and that was kind of the technology that we went for. There was actually this huge GitHub issue internally that was talking about like, why did we pick this thing? Because like a ton of people hated writing plugins with it. But it was the technology we picked because JavaScript on Windows is actually really good. So if you go to the Node.js page, they actually have binary installers for all the major operating systems. You can download the source code tarball, but like most importantly, you can actually just download a Windows installer and install Node and get it up and running through a wizard that like people on Windows normally would expect. In addition to that, like Microsoft for the last like few years have invested heavily with Node and JavaScript on the Windows platform to get it up and running, working well, making sure all the libraries and things work out of the box as a great experience on Windows. And if you have problems, like they're definitely there to like try to fix that stuff. So all those decisions help make it an obvious choice for us, even if it wasn't the technology choice we would have liked to internally as a company. And in addition to JavaScript, like Python actually has pretty good Windows support. It has a fairly decent size Windows community. And again, like they have this pattern of having Windows installers right on the Python homepage. You can go and download it and just like install Python fairly easily. And it's super popular in the academic community, SciPy, and all that stuff. Of course, if you go and look at actually installing Ruby, I think when most people get talked about like, okay, how do I set up Ruby? I'm a new Ruby user. I've never used Ruby before. You probably get told to use one of these like Ruby version managers, Ruby, RVM, and Ruby build. You know, I use RVM myself, and I know plenty of people that use all the other stuff. But of course, like all this stuff actually depends on Bash. So out of the box, this doesn't even work on Windows. And if you want to work on Windows, you have to install like Cygwin and kind of go through all that stuff to get this GNU compatible shell system. And then if you want to actually use something that is more similar to like a normal installer, you can use Ruby installer, which is this fantastic project. But this is a post from December, which wasn't even very long ago, about how the current maintainer is looking for a new maintainer to help him out, and they still don't even have like a Ruby 2.4.0 install, because it takes a bunch of time and effort and work to actually package up all this stuff to get it up and running. And this isn't even like maintained or supported by the core team, but it's not like the core team's actually against like any of this stuff. It's just we don't package up any binaries for any operating systems. We just provide the source tarball and ensure that it actually compiles and works. So that's not great. Like the install experience, not so good. We're really pushing Windows people away, whereas I feel like the Node and Python examples, like they're really embracing the fact that it's really easy to get up and started on Windows for that particular ecosystem. And there's a lot of Windows users out there. So even if you go through all these hurdles to get all that stuff running, your experience of using Ruby on those platforms, if you ever tried it or worked at like a Rails Bridge or Rails Girls, you well know that it's not great. So Nate talked a little bit about forking stuff in the last talk, but Unicorn was at least one of the more popular forking web servers out there, and it blatantly just does not support anything on Windows, and that's because I think the Ruby source code does not actually work on Windows for being able to do forks. You can't even do it, so that doesn't work. And then we have this whole like cross-platform mrbgem ecosystem with architectures, but like older versions of Nokogiri. So if you're using Nokogiri 1.4.2.1, it is a Windows-specific version of the binary to fix bugs that were in 1.4.2. You can see that it was yanked. But if you're deving on Windows and use this version and then you try to deploy it on any other Unix system, like that deployment would fail because this version doesn't actually exist on any other architecture. So there's problems that have been mostly solved, but they do exist of just like different version numbers don't match the different architectures. So potentially there are other problems of just like trying to use Windows as a development platform. And so kind of the short is that we don't really have a very healthy Windows ecosystem, if one at all. It's kind of a best effort for like, I think every gem author, because most people just aren't using Windows as a primary development platform. So now that we've kind of set the stage about like how Windows isn't great for Ruby, let's talk a little bit about mruby. So for those of you who don't know, mruby stands for Embeddable Ruby, and it's a implementation of the Ruby VM created by Matt, mainly catered towards kind of embeddable devices where you can embed this language like Lua into other languages. Commonly this is done with languages like C. It's very easy to interrupt with C with mruby, and it supports kind of the main syntax and ISO standard stuff that you would expect from Ruby. But as a big caveat, since it has to actually work with a bunch of different architectures and work on embeddable devices like Arduinos or Raspberry Pis and other things that don't have necessarily a full like Unix operating system behind it, none of the like operating system level standard library things that you're used to having in MRI exist on mruby out of the box. So you don't have stuff like file or socket or any I/O built into mruby. Things like threads or forking isn't in either, because those are operating system level features. But what you do get is you get this subset of the Ruby 2.1 syntax and language, so it feels like Ruby because it is Ruby. So you get procs, blocks, you can monkey patch, you have hash literals, like you can just write them in line or arrays, which is not true in a lot of other languages. Like if you try to write a hash in Java, you actually have to like use a constructor and then actually like index into each one individually to do that, whereas in mruby you can just do it like it is in Ruby. And since we don't actually have all this stuff in standard lib, you have to depend on some type of ecosystem to get a lot of these libraries, right? So the equivalent of mrbgems is called an mrbgem. So inside of mruby you have an mrbgem, which is this rake file that is basically just like a RubyGem rake file specification, gem specification. So you have a name, some metadata, you can add some dependencies. Should look pretty familiar for anyone who's written a RubyGem. And actually out of the mruby distribution, there is a core set of mrbgems. So since mruby is meant to be embedded, a lot of the stuff in standard lib is stripped down. So you have like a smaller version of array. If you want to access a lot of like extra fancy features like slicing and other things, you actually have to pull that in because you may not need that normally. So you don't package the kitchen sink by default. You actually slim it down to be as small as possible. So people who do need that feature can actually just bundle in mruby array extension or like the enumerator thing for things they actually need. So you can actually bundle in just the things that you need and not like everything that is in standard library, unlike MRI. And there's actually this thing called mgem list, which is kind of the central repository on GitHub that maintains a list of all the mgems that are kind of publicly accessible. And there's over 400 last time I counted, so not like a generous number, but it's not a minuscule number either. So you can get access to things like socket, XML parsing, there's a Redis client, there's a bunch of encryption stuff. And so more often than not, like a lot of the stuff I've actually been able to find for kind of day-to-day kind of things, but there are definitely other things that I've needed that kind of just aren't available. But what is kind of the state of, like we have this fresh ecosystem because you aren't just using Ruby gems, because you can't just use a Ruby gem because most Ruby gems expect standard lib to exist. So like just taking the pure code of Ruby gems and trying to run that in mruby doesn't really work super well if that library doesn't exist in mruby. So we kind of have this fresh start to be able to rebuild this ecosystem out there. And so the support of mrbgems in Windows today is not necessarily the best because most people who are writing mruby stuff come from Ruby. And that means you're taking existing Ruby code and trying to port it into mruby. So you're taking stuff from standard lib, you're probably building an interface like there's mruby.io, which is actually just a port of the IO module from standard lib as an mrbgem. And of course, that's all kind of this POSIX Unix-based format. And so we're making similar mistakes today in mrbgems. So as an example with mruby socket, Zachary Scott last year basically added a patch so it could actually compile on Windows last year. And when I was talking to him on the phone about this, he told me he actually just copied and pasted this code from Stack Overflow and then submitted a pull request, and it got merged in, and like it's from some other library that made this bunch of the socket stuff work. And so, you know, that's, if this is like the state of the art of like Windows support, it's probably not like super great. And like 2 years ago, I was doing some stuff with mrbgem. So I took someone else's mrbgem, forked it, and I was trying to get it to cross-compile on Windows. And libyaml, by default, like out of the box, if you just take the C library, it works on Windows fine. You can compile it with on Visual Studio, you can compile it with GNU and all this stuff, and it works great. But actually cross-compiling it took like many, many Friday nights, which I'm sure could have been better spent doing other things. But you have to figure out the this like YAML declare static C flag that I need to pass to actually like compile it statically. Because the --x static flag that worked on Unix just didn't work properly when I was cross-compiling because of the way it does like operating system level detection. So in order to kind of like make all this stuff work, you have to, for even C libraries that work on Windows, you have to kind of dive in and figure all these pieces out. And of course, like building inside of C is like a special place because like every C project decides to like have their own different like build tool. So you're either using CMake, AutoConf, scons, or something else, and like you basically have to fight that system and learn this new other make system every time. So that wasn't super awesome. And kind of at the end of the day, like I was saying before, we're basically taking all these existing Ruby projects and we miss them because we want to be able to do productive things, and we're just porting them over, copying the same mistakes that we're making MRI for supporting Windows, which is not super awesome. So that's kind of the short intro to mruby. And so I want to take a quick tour of Rust. I've been playing with Rust a lot recently. It's probably mostly Yehuda's fault. And for those of you who don't know, it's a systems programming language. So similar problem space as something like C or C++. So if you're writing native extensions in Ruby, you know, you're writing stuff in C. Ruby, the language itself, is written in C. And what makes it really compelling is that they make these safety guarantees about preventing seg faults and about thread safety and things that are really relevant, I guess, like in today's like multi-CPU architecture stuff. And one of the things that Yehuda really harps at me about with Rust is that it's an enabler of a language. And what I mean by that is that it enables people, a lot of people now, to pick up something like Rust who may not have been comfortable or familiar with picking up something like C and felt comfortable actually writing it. Not that C is particularly hard to pick up, but it's not easy to become good at writing C. Because Rust enables to actually write system-level programming code that works and you can feel safe about not leaking memory. And so kind of to hit this point even home even more, so Nokogiri, I'm sure many of you used it if you're using any Rails app, the XML parser that's built on top of libxml2. These are people who are pretty seasoned like C developers who are maintaining this C extension on top of libxml2. And if you just search, there are definitely like seg faults that happen. So like even people who do C on a regular basis can still make mistakes. I mean, OpenSSL, right? Like there's just tons of stuff out in the wild where this happens all the time. And these are people who program in C like every day. And so I think one of the really compelling things that Rust makes with regards to safety and with enablement is that if you can successfully compile a Rust program, it will not segfault at runtime. You may run to other problems, but it actually won't segfault. And that's a really amazing guarantee to make as a systems programming language. And the way it achieves that is through this ownership model. The fact that through compile time, it can actually track how memory is being referenced and used. So you have to write your programming in a different way, but the guarantees you get are that the compiler is actually making sure that the way you write your code is making sure you're not leaving any dangling pointers around. And the next point that is really interesting is since it's a systems programming language, it has to be fast. And so if you've ever done any systems programming language stuff, you've probably written stuff that looks fairly similar to this. This is actual Rust code. And what I'm trying to do here is fairly simple. I have an array, and I'm just trying to calculate the sum of it. And so if you're doing this in like some intro to programming class, you have this array. You're going to iterate over through the thing using some for loop, and then you're going to hold the sum in some variable. And then we'll just print the value at the end. So this is a pretty easy example. Even if you don't know any Rust, you can easily read what this is doing. But this is probably more what you're akin to in Ruby. So you have these like higher level abstractions. This again is valid to Rust. And so you can make an iterator on this array, and then you call fold, which is like inject in Ruby. And it even borrows, thanks to Yehuda, the pipe syntax for specifying the variables. And so with here, we have a starting value of 0. And we're folding over the addition of the starting of the carryover accumulator sum, and then each element value. And then at the end of it, we get the total sum value. So this one line looks much nicer and more Ruby-like than this. And this is valid Rust syntax just built in the standard library. And what's amazing about it is you aren't actually making any trade-offs here on performance by using this better abstraction, right? Like using fold is actually faster than writing the for loop. Because in Rust, the compiler now knows about the bounds of that array because you're using the iterator. So you can actually unfold the entire thing in assembly and not actually loop through it. So you don't have any of these jump calls. And the more information you give the Rust compiler, the more optimizations it can make. So that's what Rust means by having a zero-cost abstraction, is that by using these higher-level abstractions, you're not actually making performance trade-off like you would oftentimes in Ruby by using some of these other nicer functions to make your syntax look nicer. So that's really awesome. The next thing that made it really compelling for me to start looking at it seriously was that they have this focus this over in 2016 on cross-compilation, and they're betting even more on it in 2017. And so as part of it, there's this tool called RustUp, which is part of the Rust toolchain that you can use to basically manage your different versions of Rust, as well as kind of the different targets and architectures you want to compile for. So on a single host, you can actually compile, they provide 36 different architectures that you can compile to. And for interest for me, they provide a lot of the major ones that I care about. So you have 32 and 64-bit OS X, Windows on GNU and Visual Studio, as well as Muscle and GNU versions of Linux. So from my single Linux host OS, I can cross-compile to all these different versions of Rust and make libraries and binaries that are compatible. And one of the other things that was really great for me was reading the Rust up README. They have this line, they have a section called Rust up on Windows. And the first line is this thing right here where it says, Rust up works the same on Windows as it does on Unix. And so that means they're treating Windows as a first-class citizen. And Rust as a project actually works on Windows and has to because Mozilla is deploying Rust as part of Firefox now. So as of last year in Firefox 48, it was the first release of Firefox that actually ships with production Rust code. And so the piece of code they extracted to rewrite in Rust was the media player. So the media player is written using Rust, and they're able to kind of sandbox it with these safety guarantees. And they have to actually make Windows work because they're shipping it with the browser. So so Mozilla, who is the kind of main steward of Rust, is betting on Rust working on Windows. So I have a lot of confidence that using this as a base technology for getting all this stuff to work will guarantee pretty good Windows support because it means all the low-level I/O stuff has to work pretty well. In addition, they have a bunch of R&D work they're doing for browser stuff in Servo that extends beyond just the Firefox stuff. And of course, as a person who's explored other languages, one of the things I miss the most when visiting other ecosystem is bundler. Like having a good package manager is actually really crucial to being productive, being able to kind of have these guarantees of like, does my code work and will it work on someone else's machine? And having visited the C world of AutoConf and CMake and all that stuff, it was really nice to know that Yehuda and Carl helped create Cargo as well as bundler. So you see a lot of analogies in both the way it works in workflow and as kind of the common paradigms we're used in Ruby. So in Rust, you have cargo.toml, which is equivalent to your gem file. But it isn't just dynamic DSL, it just uses the toml markup. And you can kind of just specify all your dependencies that you want, like you would in your gem file. And then you have cargo build, which is a command you can run on your machine locally. And this goes, like bundle install, goes in, fetches, and resolves all the dependencies you have. So I only had 2 dependencies here, but it went and fetched all the dependencies of those dependencies and created a resolution graph for me and compiled the Rust library for me. So I don't have to do this thing and then figure out how to actually build my project. Cargo build actually does all that in one step. So like bundle install, it's like the only thing I really need to know to actually get my code to a running state. So if I'm cloning out another Rust project, it's very easy to get started once you have the toolchain. And then beyond that, you have cargo.lock, which is equivalent to your gemfile.lock. And so it has the complete dependency resolution graph built into the file, so it can be reproduced on any other person's machine. So with that knowledge, like how do we combine this mruby ecosystem and technology with kind of all these nice things that Rust brings to the table for writing systems level programming things? So I think in order to kind of appreciate some of the stuff that's happening, we have to take a look at what it looks like to write an mrbgem in C, like just the default path. And this is the typical directory structure of an mrbgem. You have, in this example, just a very simple thing where I'm just trying to print hello to the screen. So in my C source code, I'm just going to return the hello string that's generated in C and convert it into mruby. So we have this C file. So inside the source directory, you can put any number of C files, and you can call them whatever you want. And the mruby build tool will actually go through and compile all that stuff for you. So here's the mruby C file that I generated. And you need these 2 classes, init and final. So gem init is basically where you kind of construct all the stuff at startup. So you're going to define your modules and classes that you want to be able to work with in C. So in this case, I am defining the hello module, calling this mruby define module that's part of the mruby C API. And then I can define any number of class or instance level methods on top of it. I can define any other classes as well. And I'm making it call this other C function as the implementation, and then you have to specify the number of arguments. In this case, I don't have any, so I can use mrb args none. In the final state, since we're in C and we have to manage our own memory here, you have to do any cleanup work that's not managed by the mrbgem, because mruby is garbage collected, inside of here. So I don't really have any dangling pointers that aren't going to be managed by mruby here, so I don't really have to do anything here. And then finally, we just have the C code that's actually being called when I call hello. And this is just a very simple thing. We're taking a C string and we're just converting it to an mruby string, and then that way it's accessible inside the mrbgem. And with that, we can actually just call hello.hello inside of mruby like it was any other Ruby code. So that's pretty nice and easy to do, and that's kind of just how native extensions or native mrbgems work in mruby. And so to make this work with Rust, one of the nice things that Rust brings to the table is it has a really nice FFI system. It's able to, at no cost, actually just generate C-compatible code. So when you're compiling Rust, you set the property nomangle above the method that you want. So Rust doesn't try to make any optimizations and knows to leave this function in that address space and not mess with any of the names or anything. And then you need to extern it to make it available as a public method. So with this code, inside of any C object, so if I have this Rust library, inside of any C code, I can actually just call double input, pass in a 32-bit integer, and it will work like I wrote it in C. But the nice thing is I actually get all the safety and other guarantees of the Rust library from within inside of C, because Rust makes those things at compile time. So that's really nice. And so if I were to take that same example and try to write it in Rust, I'm going to create a Rust folder. And I'm going to have a cargo.toml, but I don't have any other things there. And I just have this lib.rs for the source code for Rust. And so in here, you see similar structures here. So I have the nomangle. So these function names are just the same as they would be called in C. And one of the reasons I have these unsafe blocks here is because in Rust, with the ownership model, you have to be able to tell the compiler, hey, I'm not actually responsible for the life cycle of these objects called inside this block. Since this is a C call, like you're actually responsible, or someone's responsible for managing the life cycle of these objects, and the compiler is not. So you're telling the compiler, hey, I know what I'm doing, don't worry about it, this stuff will get cleaned up, and you don't have to worry about this at compile time. So since I'm making basically these C API calls from mruby, the C API, I need to wrap them in these unsafe blocks. So similar to the C code, I'm just defining a module called Rust. I'm putting in this class, and then I'm telling it to use this function that is built in Rust, but will look like a C function when it's actually compiled. So you have the init, the final, and the actual Rust implementation, and that will get you to hello world with Rust and mruby. In order to do that, I actually had to create a wrapper library called mruby to actually wrap parts of the mruby C API to make them available in Rust. And so what mruby is it's this Rust binding around the mruby C API, and it's actually split up into two crates, where crates are basically the package, the name of the packaging in Rust, and one mrbgem. And so the reason I did this is because I wanted to split up kind of low-level implementation and like kind of higher-level abstractions. So there's libmruby sys, which is the low-level implementation. And this defines basically all of the kind of signatures that I want to be able to access inside of Rust. So if you notice in this lib.rs file, there is no body, like actual code implementation, besides the function signatures. So all the actual implementation is in C, and I'm just defining it in Rust so Rust knows about it. And so, for instance, this mrb defined module is something that we called in that hello world example. And it's the same signature as the C code because it's just calling the C code here. So that's what libmruby sys is. And then we have this other crate called mruby, which is kind of the higher level abstraction that sits on top of this. And so the reason to create this is because you don't want to actually make all these method calls every time you're doing a bunch of things. And so you can create these higher level function calls that actually wrap all the unsafe code and allow you to just call proper Rust code. So this function basically takes a mruby string from the mrbgem and converts it into a Rust string so we can use it with other Rust data structures, methods, and things like that. And I didn't want to basically do all this slicing and kind of raw C pointer manipulation every time I want to manipulate a string, because that happens basically all the time. And so one of the nice things is since all this stuff, all the unsafe code is here in this method here, inside of Rust, I don't actually have to, when I'm using this library, wrap this function in an unsafe thing, because that's handled inside of this method. So over time, I'll be pulling more things into the higher level abstraction as I figure out the API that I want there, and slowly removing like the manual calls to the mrbc API directly. And then finally, we need an mrbgem for the mrbgem to link against. This allows us to basically use the right version of mruby that you're using locally, so it's using the right version of the API and the right headers and things, and not just some random. So if you ever done any of the Ruby debugger stuff, like it actually bundles the entire like header stuff into the gem, and every time a new version of Ruby comes out, it like breaks the debugger because like some APIs and stuff change. So the nice thing about this is that I'm actually linking against the version of mruby that you have locally, so I don't actually have to vendor any of that stuff into my mrbgem. And so inside of, if you've ever dug into the mruby or the Ruby source code, you've noticed that basically there's a ton of like C pound define like macros all over the place. Like Mats uses this like everywhere. So mruby's not unique in this, like it basically does the same thing. But unfortunately, all these pound define preprocessors aren't actually available across FFI. So it's not publicly available to me inside of Rust or any other language that wants to use the FFI interface. So we actually have to wrap all the macros that we want from C in actual C functions, so they're publicly available to Rust to actually map to. So this M for Ruby runtime actually just takes all that stuff and wraps them in actual C code to be used. So with that, I can actually access this thing inside of the libmrubsys crate, because now they're publicly available C methods. And so I did that really simple hello world example, but that's like really trivial to actually write, and it doesn't do very much. So one of the things I wanted to do was take a library that wasn't super complicated, but was actually a real world practical thing to be done. So if you're familiar with all the .op project, it came out from the Python community, and it looks something like this. Like Cargo uses it for its option parsing, so it's an option parsing library. And one of the neat things it does is it actually allows you to define as a string the usage that you're going to do, and then you pass in your array of arguments, and then it'll actually then return an options hash or map of some sort for you based off of this usage thing that you can print as help and then the argument list. So it's really neat, so you don't have to kind of do all that stuff by hand. And there's a bunch of different implementations of it across all the languages. The Rust one is one of the most up-to-date ones, and it's well-maintained because Cargo depends on it. But when Christoph and I actually were starting to implement it and looking at it, there was a C one that wasn't well-maintained or up-to-date, and there was a Ruby one that we were thinking about porting from, but that I think there hasn't been commit to in like 3 years. So there's been a bunch of changes, and it didn't actually have a lot of the new features that were part of .op. So we actually chose to use C++ as the initial implementation. So we wrote a C++ wrapper in mrbgems around it. And Christoph at the time, I think, was doing still C++ as part of full-time. And you can see, like, we actually just made a simple mistake. We missed this break. And it's like, for people who do this stuff, it's like still possible to make these mistakes in code. And all we had to do was write a wrapper around the existing C++ library to make it available inside of Ruby. And we were still able to, in the like less than 100 lines, like a simple like forgot to put this break in and it caused seg faults. So the real implementation of mruby docop still today is in C++. And so knowing all that, I wanted to take this thing and try to use the docop Rust library and see if I could build this mruby docop thing based off the C++ implementation. So in mruby, this is how you use it. You have a usage thing. You just have a here doc. And then you just call it, right? Like, so for the C++ implementation, just call docopt as a module. It takes a class level, it has a class level method called parse, pass in the usage, and then you pass in kind of all the argv arguments that you're going to have on the command line. And then once you do that, you have access to kind of this options thing that you can index into get, see if it actually was used or not. So if detect Ruby command was run, this will return true. If not, it will return false. And there'll be ones for all the other commands that I have. So this is the parse implementation inside of with Rust for that document. And the way this works, you don't have to necessarily read it line by line, is that you kind of have to be able to parse out. So if you were to do this in C, you would have to actually parse out the arguments. So you have to get both the string and the array and then kind of assign them to these locations in memory. And once you have that, you have to basically convert this stuff into Rust objects to be able to pass into the docop Rust library. So the first thing we're doing, we're calling that high-level mruby string to Rust thing to convert the mruby string to Rust. And then we need to create a equivalent array / vector list object that will get passed to docopt based off of the mruby array. So we're calling a bunch of C-level methods to actually extract these values. With that, we can actually then call, so this actually calls the docopt library. And with that, we take the usage and we take that thing we just created and we get kind of the data structure that Rust gives back to actually see whether options are being correct, what options have actually been passed properly. And with that, we can use the data object allocation. So this is allows us to basically store the Rust, since it's just a allocation inside of memory, it stores it inside of mruby. And so it tells Rust, well, it doesn't tell Rust, it tells mruby that, hey, we have this data structure. You don't know how to access this thing, but here, keep this in memory. And so the reason to do something like this is because you don't necessarily want to do this conversion back and forth between mruby to Rust and back from Rust to mruby all the time. Because there's a performance cost from doing that typecasting construction, basically. So in MRI, there's plenty of C extensions that do similar things. Probably the most common one that comes to my mind is Nokigiri. So when you're parsing XML documents, it doesn't actually convert that whole thing back into a Ruby data structure. It actually just provides C functions that are accessible by Ruby to actually access that data structure from your Ruby code. So that's what I'm doing here. So I'm actually keeping this argv map a Rust data structure around, and then I can access it as if it was a normal Ruby data structure. So if we look back at the Ruby code, that was the implementation of parse, and so this actually just looks like a hash, but it actually isn't a Ruby hash at all. So that's all we had to do to actually get that to work. And then as a user, like, you don't actually have to know that you were using Rust at all, right? Like, this is the code you're using. It just looks like any other standard Ruby library. It could have been written in Ruby for all you know. And then to pull it in, you just add it in like any other dependency, and it will build and compile. So it's kind of just like the whirlwind tour of like how to get all this stuff working and running. And what's great is all that stuff compiles and works on Linux, OS X, and Windows, like out of the box. Like the CLI, it's a native extension. I didn't have to write any Windows-specific code to make it work. Like, it just compiled and worked. And so some of the stuff that I was talking about before, so things that I still need to work on is the Rust C Ruby wrapper. I need to add more of the mrbc API. So currently I've only done stuff that I needed to actually get docop to work, because that was the only way I could actually test whether the APIs work properly. And then I need to also go through and abstract more and more of the higher level the low-level things into a high-level abstraction, so you actually should be able to write an entire library without calling any unsafe blocks inside of your actual library. Beyond that, I think where it starts to get more and more exciting is the fact that with all this stuff done, we can now actually start to write mrbgems around low-level Rust libraries. So there's a project called Tokyo in Rust, and it's actually a low-level networking library written in Rust. And one of the nice things is, like, unlike mruby socket, if we were to write a wrapper around Tokyo, it would actually just work on Windows. We wouldn't have to write in that stuff. We can actually kind of delegate all that work into the Rust ecosystem. And they have a bunch of low-level libraries out there that we can do that with. And so this is where all this gets promising. So same thing with file I/O, right? Like, I don't want to use mruby I/O if I can use another thing that actually just works super well on Windows and doesn't have any caveats. And so that's kind of the future direction of where I want to take all this stuff, is like we can build an entire ecosystem around using this expansive existing low-level systems programming ecosystem of experts who've been doing this stuff because they have to make it work for Firefox and other things. I don't know if any of you have heard of the Helix project, but it's a thing that Yehuda and Godfrey have been working on that basically is a lot of this similar stuff, but all for MRI. So being able to write native extensions for your MRI code inside of Rust is what Helix is about. And so some great use cases would be you could take parts of Rails or sold parts of your code base after you profiled it, rewrite that in Rust, which is this systems programming language that is higher level to work with, and you're not segfaulting. And be able to do that, add that into your gem file and make that work. And so the reason that's important is mostly that we're hoping to integrate all my m4ruby stuff into Helix eventually and have a single code base and have this kind of like common Ruby, universal Ruby thing where no matter if you're using Ruby or MRI, you're able to kind of do all this Rust stuff with the same abstractions with it. So kind of in conclusion, I think we all know that Ruby doesn't have a great history with Windows. We're pushing tons of Windows users away, and there's a lot of them out there. And it's really just unfortunate, I think, for us, because it makes it hard to grow the ecosystem of potential people who should be using Ruby, because it's a great language with great people and a great set of libraries and things to make you productive. And mruby has an opportunity to have a fresh start. It is a new ecosystem. It's only 5 years old. There aren't a ton of people working on it. And that means we don't have to follow in the same footsteps of MRI. Like at this point, like to change the entire mrbgems ecosystem would be really hard, right? Like there's just so much stuff out there today. And I think finally, like with a lot of the stuff that Rust has cared about, we can create a ecosystem with this to make a Windows-friendly ecosystem that is inclusive of everyone and not just people who are primarily users of Unix. So if you're interested, I'd be happy to talk about this more online or in person, but I'm very excited to hopefully make the Ruby ecosystem better for everyone and not just people who are on Unix. Thank you. Questions? I have 7 minutes. Yes?
Is mruby from scratch rewrite or core book or MIR?
It's written from the ground up. So it doesn't. One of the benefits of doing that, besides, so you lose tons of backwards compatibility, but one of the benefits was that the mruby C API is significantly better, cleaner, and simpler than the Ruby C API. So you don't have all the sacred cows that you do in Ruby today. And that also means my work for the m4ruby stuff is significantly easier than Yehuda and Godfrey's work for Helix, because the Ruby C API was built like 15 years ago. And mruby was given the chance, like Matt's was like, well, if I could do it again, how would I do it? And so there's some nice things that you see in the C code if you've looked at both of them, where you're like, yeah, that kind of sucks that you can't change that. So yeah, to answer your question. Yes?
Maybe mruby instead of a subset of Ruby, the base of Ruby?
So your question was, could mruby become the
standard base.
the standard base for Ruby instead of a subset of it? I mean, I feel like if you were to do that, you'd be basically replacing the entire ecosystem there. And that doesn't mean it's impossible, but there's a lot of stuff that has happened in Ruby, and you'd be throwing stuff like Rails and Rack and all that stuff out the door. But I mean, in theory, like if you had common Ruby stuff, there is a potential, I guess, like vision where you could write code that works on both MRI and mruby. And in that state, I think that would be significantly easier, but that's nowhere near close to where it is today. Yes?
Is there motivation to put more core features of mruby into Rust? Or just libraries?
There's no, I think, so to repeat the question, is there incentive to put more core features of mruby into Rust or just libraries? And as far as I know today, like there's no incentive on the core team for, well, there isn't really a core team in mruby. It's really just Mats and people who are helping him. But there's no like incentive because the whole team is like, everything's built around C like it is for MRI. Like I think all the core level stuff is going to maintain its C nature, and there aren't really plans to change that. I'm hoping with some of the stuff, if we're able to deliver on half the things that I've talked about in that last part of my talk, that there will be an interest in the ecosystem to embrace stuff like Rust and make it easier. But yeah, there aren't really any incentives internally to kind of change where things are today.
Another question? Yeah, please.
Yeah, does the mrbgem can it be compared to the MRI VM or like speed-wise, and are there big differences?
So the question was, can the mrbgem be compared to the MRI VM speed-wise and other differences? Is that? Yeah. Okay. So there are definitely a lot less people working on mruby, and since it's written from the ground up, it's very different. I think by intentionally, since it's embedded, it has different constraints. Nate touched on this, I think, in the Q&A, about just like how Ruby is kind of this very general purpose thing, and you have very opposite kind of use cases, right? Like you have the Rails app, which I think like 80% of the people that probably do Ruby are using it for, right? Like whether it's Rails or some other type of long-running daemon process that's very Java-like, right? And those constraints and concerns have very different defaults than you want if you are I am a script, like at Heroku we use as part of the build pack, like Ruby, and it's a very short-lived process, right? Like it runs maybe 15 minutes max, and then we kill it if it runs longer than that. And so it definitely doesn't run nearly as long, and it's not allocating nearly as much memory, doesn't have kind of the same constraints, where things like in Rails, fast boot up time is nice, but it's not a hard requirement, whereas like fast boot up time for a scripting thing is actually super important. So I think mruby is not designed in nature to be run like it is for Rails. And so it makes a lot of trade-offs with even the data structures and stuff. Like data structures, like when you allocate an array in mruby, it allocates significantly less space, and it takes up less space because it has to be able to be run on an Arduino, right? Like it has those kind of constraints. The benefits of that is if you're using mruby for things like tooling or scripting and things like that, you get massive speedups because it takes an order of magnitude less time to boot up an mruby VM than it does an MRI VM even before you pull Ruby gems in, right? And not to mention the fact that since you can compile stuff down, you actually don't have the require load problem, which you do on MRI. The flip side of that is the runtime doesn't have nearly as many optimizations in the garbage collector or other things. So the MRI garbage collector is way more mature. It's been around a longer time, and it has to have adapted and evolved for the Rails use case. So there are, I think, things where people are looking at like running mruby as long-running things, but it's for like IoT devices, which definitely have totally different performance constraints than running them on like a bunch of racks, right? Like to power like the next Google or something, right? So. Hope that answers your question.
It's it.
Awesome.
Thank you
Yeah.
very much.
Thank you.